Hey guys, welcome to the weather breakdown. Time for another deep dive this time. So this time we are going to talk about the origin of supercell updraft rotation. In short, where do supercells actually get their rotation from? What makes them spin? Because a supercell is an updraft which is spinning cyclonically, or in the northern hemisphere, more spinning cyclonically. So we're going to see how that comes about. Where does this supercell get its rotation from? It's a very interesting topic, sometimes wildly misunderstood, so I'm going to try and break it down for you guys. Don't be disheartened by it. I am going to pull some math into the picture, but the math is rather easy to understand, even if the symbols might give you a headache. But don't worry, I will pull you through it. So without further ado, let's dive straight in and see how do supercells actually start to rotate and which elements need to be present for supercell rotation to be possible. Let's dive straight in. Now, in order to understand how supercells get their rotation, we must first understand what rotation is. And in meteorology, rotation is referred to as vorticity. And vorticity can be explained in the following manner, for example. Say you, for example, say you have an XY plane, right? X here, Y here, right? And you have a wind flow here with the maximum wind in the center and minimum wind the more you go away from the center, right? Vorticity states that if you put a pinwheel in here, that this pinwheel will start to rotate in this sense. Why in this sense? Well, it's not too difficult to understand. The maximum wind here, which is slower than the maximum wind to the north, because this is east, this is north. Or latitude, longitude. Okay, so if you have the maximum wind here, which is slower than here, there's a delta between the two. So this one will start to rotate in this manner. Conversely, you have the same thing here. Maximum wind is now here to the north, while the minimum wind is to its south. There's a delta here between the two also, meaning that this one will rotate in a different sense because the wind maximum separates the two here. This one spinning counterclockwise, which is called positive, and this one spinning clockwise, negative. So this is positive vorticity, negative vorticity. Meteorologists call this horizontal shear vorticity. Why shear and horizontal? Well, it's a horizontal airflow, right? And there is a horizontal difference in speed. This moves faster than this one, which means there's horizontal wind shear. Now, there's another type of vorticity that we can consider in an XY plane. So let's draw that one. If you have, for example, again, an XY plane, X like this, Y like this, and you have airflow, which moves in a curve like this, right? Which moves in a curve like this. Wind speed is slower here than it's here because the vectors are longer, right? Again, it's the same story. If you put a pinwheel in here, right, in the center, it will start to rotate like this. Okay. Now, this is no longer shear vorticity, but it's actually another type of vorticity, which meteorologists like to call horizontal curvature vorticity. No longer vorticity caused by horizontal shear per se, but actually because it moves in a curvature. It curves around a certain point, right? And the total vorticity of a system is actually this one added to this one. If you add these two together, you have your total vorticity in your system. Now, if we draw this a little bit in a more three-dimensional sense, okay, let me draw it then that way. So I'm going to draw a line here, which this one presents the z-axis. So z height, the more you go up into the atmosphere, height increases. Okay, you have an x plane, right? And you have a y plane, right? So this is east, this is north, and this is up. Okay. Now, say for example, you have you have vorticity. There's some curvature vorticity here. There's some shear vorticity. They both add up to some type of vorticity like this in a cyclonical sense, right? Positive vorticity, okay? Now, the axis around which vorticity happens is what meteorologists call the vorticity vector. The vorticity vector can be written like this. They call it omega, right? And omega is either has a vertical axis or has a horizontal axis. And the axis around which vorticity happens dictates whether it's vertical or horizontal. And since the rotation here happens around a vertical axis, this is what's called vertical vorticity. Positive vertical vorticity. Why? Because it spins cyclonically. So let us get this out of the bag too. Positive vertical vorticity. You can easily see this as follows. You have in physics called the right-hand rule. And the right-hand rule states that curl your fingers in the direction of rotation, your thumb will point up. So, thumbs up, it's positive vertical vorticity. Conversely, if you have, for example, rotation again somewhere else, right? But this rotation spins now clockwise, okay? The axis of rotation is still vertical, but follow the right-hand rule now. Curl your fingers inside the direction of rotation. Your thumb will now point downward, right? Your thumb will now point downward, thumbs down for this, which means that this one is called negative vertical vorticity. Even if it's around the same axis, it's still vertical vorticity because the axis is along the z-axis here, right? Negative vorticity is vorticity spinning clockwise around the vertical axis. Vorticity spinning counterclockwise around the vertical axis is called positive vertical vorticity. So now we've handled the vertical here, but there's also another one, the horizontal. So let's erase everything and draw horizontal vorticity, okay? It's a little bit the same story, not many difference between the XY plane and the vertical vorticity, but bear with me here. You have the z-axis here, which goes up. Height goes up the more you move away from the ground here. This is the X plane. This is the Y plane, all right? Again, this is east. This is Y, this is north, and this is Z, this is up. Okay? Now bear with me here. We've already understood now that if you have wind which increases, for example, we all know what the vertical shear is. Vertical shear is wind speed that increases with height the more you go up into the atmosphere, or increases in speed, sorry, the more you go up into the atmosphere. If you look at this now, this is also shear vorticity, but now no longer horizontal, but vertical shear. You have vertical shear. Why? Wind speed increases with height. Okay, the more you go up, and wind speed increases in speed, the more you go up into the atmosphere. Put a tube in here. Okay, this tube will also start to exhibit rotation or vorticity in this sense. Why? It's again easy to understand. At the top of the tube, wind speed rushes faster than at the bottom. Again, there's a delta here, meaning that this tube will start to spin in this direction. Okay? And again, if we follow the right-hand rule, curl your fingers inside the direction of rotation. The direction your thumb points is your vorticity vector. Right now, the vorticity vector points like this, right, in a horizontal sense. And if your vorticity vector points in a horizontal sense, again, omega, you have vertical, but you also have horizontal. The vorticity vector, if it points horizontal, like this is what meteorologists call horizontal vorticity. So we now covered the vector quantity omega, which is the vorticity vector. We've talked about the vertical one and the horizontal one. So now we actually know what vertical vorticity is. We know what horizontal vorticity is. Horizontal vorticity is vorticity along a horizontal axis. Vertical vorticity is vorticity around a vertical axis. So let's now continue a little bit further and see what this means in terms of supercells. And by the way, think about it. We need an updraft for a storm, and we need that updraft to exhibit vorticity in a vertical sense, right? Why? Because you have a vertical updraft, and we want that updraft to start spinning, right? We already know right-hand rule, curl your fingers in the direction of rotation, the thumb point upward, meaning that we need positive vertical vorticity in order to have a mesocyclone. Cyclone, cyclonical, you get it, right? Vertical vorticity in meteorology is called zeta. Okay, so we're now going to talk a little bit further about it. I'm going to pull a little bit of math into it. It may sound daunting at first, but don't worry, I'll pull you through it. And then after we've done our theory, we are going to apply it to a conceptual diagram of a supercell. Now, with vorticity out of the way now, we can continue our discussion how supercells get their rotation, or where do they get their rotation from. So bear with me now. You're at a certain location, okay? And you have a magic wand. And you can magically conjure a thunderstorm right above your head. And if you want that thunderstorm to exhibit vorticity, or to exhibit rotation, you need to have a vertical vorticity, vorticity around a vertical axis, okay, to coexist or to be co-located with that thunderstorm updraft. Because if there is vertical vorticity at the same location where the updraft is, it will go up in a helical flow, right? Which is actually what a supercell is. It's a rotating updraft, okay? Now, this means that at your location, right, you want vorticity to increase, okay? Either from zero vorticity or not enough vorticity, but the end goal is you want as much vorticity as you can get in order for the updraft to be co-located with it so that it can exhibit rotation. Okay. In meteorology, we need to start looking at the vorticity tendency equation, which is an equation that governs how much vorticity at a certain point increases. Okay. So we're going to delve into that right now. It's a little bit math intensive, but don't worry, I will guide you through it. It's rather easy to understand, although the symbols might seem a little bit daunting at first. So we're going to put that out of the way, continue with our discussion, and then apply what we have uncovered to a conceptual diagram of a supercell thunderstorm. Okay, so let's dive straight in. Say that you're at a certain location, okay, and you have your magic wand. You invoke a thunderstorm right above your head. You want vorticity to be co-located at your location where you invoke that thunderstorm in order for the thunderstorm to exhibit rotation. Okay, now this is what the vorticity tendency equation tells you how that's possible. Okay, so this one is called the vorticity tendency equation, right? Now this one here, d zeta dt, we already uncovered that vertical vorticity is called zeta in meteorology. So this one states the local change, right, of vertical vorticity over time, right? This is what you want, right? You want the local change of vertical vorticity over time at your location to increase. So you want this one to increase. Okay. Now, this one here, the local change of vertical vorticity over time, is governed by three parts. This part is called the advection of vertical vorticity towards your location. This one is called the stretching of vertical vorticity, right? And this one is called tilting of horizontal omega sub h of horizontal vorticity into the vertical sense, because you want vertical vorticity. Now, say, for example, we've already know that vorticity or vertical vorticity in meteorology is a zeta, right? You see a zeta in here, you see a zeta in here, right? Which means that these aspects of the vorticity tendency equation, they need zeta to begin with. So say, for example, there's no vorticity at all at your location, which means that this one, zeta, is 0. Here, zeta is 0 too, right? So essentially, this means that this whole term is 0. No vorticity here, which means this whole term is also 0. If you don't have vorticity in the stretching term here, I mean, there's nothing to stretch. If there's 0 vorticity here in the advection, yeah, you don't have anything to advect. The only term that's left is this term, and you can see here, zeta is nowhere to be found here, which means that this one is the only term in the whole supercell equation, as I'd like to call it. It's a vorticity tendency equation, but let's call it the supercell equation for now. This whole term is the only one, the only term that can actually generate vertical vorticity. Why? It tilts horizontal vorticity into the vertical. We've already, in our previous section of the video, we added a tube, right? And due to the wind speed increasing with height, we've identified that this tube will start to exhibit rotation, right? We want this tube now, right? Instead of horizontal, we want this to become vertical, which means that if you now look at it, here it rotates like this, 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 here like this, here like this, and here like this. So we went from horizontal vorticity to vertical vorticity. And why would you be able to do that? Well, put an updraft in here. Right? So we'll put an updraft in here, and because of the updraft of the storm, it tilts this horizontal vorticity into the vertical. So we went from horizontal vorticity to vertical vorticity, but we'll talk about that a little bit later. We're going to further our understanding now in the notion that there's no vertical vorticity to begin with. If there's no vorticity to begin with, we already identified this term and this term is 0, right? So this term here, we can completely ignore as it's 0. This term here, since there's no zeta to begin with, is also 0. So the only one that's left is this one here, this one, right? We can rewrite this one in its I and j components, okay, where you can see here two things, du dz and dv dz. And if you think about math now, we've been thinking about math the whole time now, but if you think about basics of vector math, okay, if you have an xy plane, right, xy, this means like east to west, and y meaning south to north, right? If you have a vector, let's draw a vector now. If you have a vector, right, in that space, okay, this the wind speed, the south-north wind speed is called v component of your vector. The east-west wind is called the u component of your vector, which means that if you have a vector, say for example to the northeast, it has a v component, right here. It has a v component and it has a u component. Okay, so this is what you can see here. Okay, du dz. If you go up in z, right, the higher you go up into the atmosphere, and du dz is positive, this means that if you go up into the atmosphere, the east-west wind will increase in speed. Okay, the same holds true for dv dz here. If you go up in z, the higher you go up into the atmosphere, if you want dv dz to be positive, okay, you want the south-north wind or the v component to increase. Okay, so in order to continue our understanding, we're going to make it ourselves a little bit more easy, and we're going to completely discard the north-south or south-northbound wind. We're going to completely eliminate that one so that that term is zero, as you can see here. You have the w dx times zero. Okay, the w dx times zero is zero, so we can completely ignore this term. I have a minus sign here. Minus times minus is positive. So the only one that you end up with is this one. Don't be afraid what it looks like, what it sounds like. We're going to break this one down when we're going to apply this to a conceptual diagram. Okay, so let's dive straight into that one right now. So by now, I hope I didn't scare you off with the math. I'm telling you it'll be a little bit more visual from now on. So with that out of the way, if you like what I do, please drop a comment in the comment section to say what you thought about the video. Also, don't forget to subscribe if you want to be notified of new content, okay? The next video isn't going to be a deep dive, more of a forecast, but if you want to be notified of any new content anyway, do subscribe because new content is coming out, okay? So let's continue our discussion now and hope you liked the video so far. See you on the flip side, guys. So we're now where we left off, where we have the remainder of our supercell equation here, where we have two terms, du dz and dw dy. Okay, we multiply these two to get the local change of vorticity over time at a given location. So we're now going to break these terms down, this one here and this one here, namely du dz and dw dy. Okay, since we multiply these, the sign of these is important. So if you multiply this one being positive, this one being positive, this means that the local change of vertical vorticity over time is going to be positive as well. Right? Conversely, if, for example, the dw dy is positive and du dz is negative, then the result here will be negative. Okay? Which means that there's going to be negative vertical vorticity. But we want positive vertical vorticity because we want the mesocyclone, cyclonical circulation. Mesocyclone meaning positive vertical vorticity. So what we want is we want this one here, right, to be positive. Here, this one needs to be positive. Okay, and the only way in which you can make this one positive is that either these two are both negative, right? Negative times negative is positive, or they are both positive, right? Then the result is also positive. If one of them is negative, we will never get a positive sign here, right? Basic math. So we want this one to be positive, okay? This is what we want. So let's erase this thing now, right? Let's erase these, okay? And let's continue our discussion. I'm going to be a little bit of a recapitulation now. So I'm going to draw a diagram again where this is the z-axis, right? If you move up into the atmosphere, yeah, your height increases, right? Oh, pretty obvious, right? We have an x-plane, right? And we have a y-plane, okay? We already know now this one is the west to east wind, right? Which is pointing east, right? This direction is pointing east, okay? This is y, okay? And this is the south to north direction, right? And again, this axis is up, okay? Now, du dz, what does that mean? Right? What does that mean? We know from a previous section of the video that u is actually the u component of the wind. right? U component of the wind, meaning the east-west wind, or the west-east wind rather, right? If you want the UDZ to be positive, bear with me. If you go up in Z, if the Z goes up, right? So if you go up in Z, DZ will go up, okay? And we want vertical wind shear, right? Let me draw this in here. Vertical wind shear, it means the more you go up into the atmosphere, wind speed increases, and we're only considering the U component, the west-east wind, okay? If you draw that, right? If you go up in Z, wind speed goes up in Z. This means that the UDZ is positive, right? If you go up in Z and the wind speed goes up, this means that this whole term is going to be positive, right? This whole term here is going to be positive, which is exactly what we've drawn here, right? Now again, put a tube in here, right? Along the y-axis, right? Put a tube in here. This tube will start to exhibit rotation, right? In this sense, like this, right? Like so. Again, recapitulation. I like to repeat what I say. Why is it rotating? Well, because if you look at that flow, right, at the top of the tube, wind speed is faster than below the tube. There's a delta in between here, as you can see, which means there is indeed rotation, right? Now, we've uncovered this one, all right? Since the UDZ is positive, there is horizontal vorticity, right? Put a tube in here, it will start to rotate, okay? Which means the UDZ is positive. Now let's look at this one here. The WDY. What does that mean? We already know that U is this component of the wind, right? The west-east component of the wind. But what is W here? What is W? Well, W in meteorology is actually referring to the vertical velocity, right? Here, this is the vertical velocity. So we want along the y-axis here, right, the vertical velocity to increase. Right now, we don't see this anywhere, but we're going to draw this right now. So let's redraw everything. I'm going to draw almost the same thing, but a little bit bigger, right? I'm going to erase everything. So let me draw now the exact same thing, okay, but bigger. Right? This is, again, our z-axis. The more you go up into the atmosphere, it goes up, right? A little bit long, right? And we have our x-plane here, and we have our y-plane, right? Again, this is west to east. This is south to north, right? This one is pointing north. This one is pointing east, right? And this one, as we've already uncovered, points upward, okay? We know, again, the UDZ is positive, or we want the UDZ to be positive, right? This one is positive. This means that if this one is positive, this means that if you go upward into the atmosphere, wind speed starts to increase, right? Which is exactly what we want, okay? Now, we want along the y-axis here, right, the WDY to increase, right? Now let's draw a thunderstorm here, right? Let us draw a thunderstorm here. There's a thunderstorm growing here, a thermodynamic updraft. All right. Now bear with me what happens now. If you put our tube now, right? So dW dy is positive. This means that dW dy is positive. This means that W here, right? W, right, is positive, is bigger than 0, right? Because as we've already know now, W is vertical velocity, right? So if you want a thermodynamic updraft, I mean, there's vertical velocity, obviously, otherwise you don't have an updraft, right? Which means that W is greater than 0. There is vertical velocity here. There is a cloud growing, okay? So if you put our tube now, right, our wonderful tube, right, which is normally, since du dz is positive, right, you would have a tube along here, right, as we have already uncovered. Put a tube in here, right? It starts to exhibit rotation, right? Like this, right? We've already uncovered this, huh? Nothing new here, right? But we now have an updraft here, which changes the situation, okay? So let me erase all these things here that I've just drawn, right? Not the cloud, right? Ah, crap. Not the cloud. I want this one, yeah, like this, okay? So let's redraw our tube with the thunderstorm now there, because the thunderstorm has implications on our tube. So if we now draw our tube again, right? I'm going to draw a tube here, and what you can see here is here it starts to increase, here it starts to die down, and here it goes like this again, right? Why is that? Remember our tilting term? The tilting term says that we want horizontal vorticity tilted into the vertical, which is exactly what this thunderstorm is doing. We have a flow here, right? We have our tube here, which let me draw my vorticity vectors again, right? You have a tube here, du dz is positive throughout the whole depth of the atmosphere, meaning that this tube here will start to exhibit rotation. But now, right, the updraft here, the thermodynamic updraft, is tilting this one in the vertical here, right? Conversely, right, across the center of the subdraft, right, to the right of it, or to the north of it rather, right, the vorticity changed direction, right? And away from the updraft, du dz is still everywhere positive, right? So the sense of rotation is again as it was here, right? And this is very important right now, because if we now look at this term here, dw dy, right, here, this one, dw dy, this means the following. The more we go up in y, right, along the y-axis, okay, let me take a color here that I didn't choose yet, like, for example, green, all right? If we go up in y, so dy goes up, right? We want this one to be positive, so this means that the w also needs to be positive, right? Positive, positive, which means this one will be positive, right? So if we go up in y, right, the more we go up in y, up until the center of this updraft, right? If you go up in y, right, the w goes up as well. The more you go up in y, the more you go into the center of the updraft where the vertical vorticity is maximized, right? This means that on this side of the updraft here, the left side or the south side of the updraft, right, you get positive vertical vorticity. Why? Increase in y, w increases as well, which means that dw dy increases, right? This here is positive vorticity, and you can see it also by the direction of rotation. It's cyclonical here, right? Which means on this side, dw dy is positive, okay? Now, if you go away from the center of the updraft, you move away from the maximum of vertical velocity until you pass a region outside of the updraft, right, where w is 0 again, right? Meaning that on this side here, if you move away from the center of the updraft, on this side, right, you actually have negative vertical vorticity, which is what this term shows, right? Move away. If you go up in y, right, dw decreases. So this one is plus, this one is negative, the whole term will be negative, right? Which is exactly what you see here. And you can see this also by the direction of rotation, which is now clockwise. So you have negative vorticity here. And this is exactly what we want, right? We want a mesocyclone to form. So this is how we do it. We have an updraft, which tilts the horizontal vorticity because of du dz being positive everywhere throughout the complete depth of the atmospheric column, right? We start with initial horizontal vorticity. We put in thermodynamic updraft in here, and it pulls this horizontal vorticity into the vertical. And this blue line is what in meteorology calls, or in fluid dynamics rather, it's called a streamline. Right? A streamline. And a streamline you need to see as a line that never breaks or snaps. It's always there. It always stays intact. And this is why the streamline stays intact throughout its whole trajectory here. Right? So we're going to talk about that right now. Everything that we have now been discussing, we now know what the thermodynamic updraft brings. It tilts the horizontal vorticity into the vertical. We know what dw dy is now, right? The more you go up along the y-axis, the more w should increase if you want dw dy to be positive, which is exactly what this is. Move along the y-axis, w increases. Move away from the center of the updraft, move along the y-axis, vorticity decreases, right? Which is exactly what we see here, okay? This is why the signs are so important. But let's now continue our discussion and apply this to a conceptual diagram of a real thunderstorm where everything will fall into place, okay? Hope you liked it this far. We're almost there. Hang on, guys. So, guys, now it's time to put everything together. So what you see here is a conceptual diagram of a supercell. And we have the same things as I've drawn in my conceptual diagrams. We have the z-axis here. The more you go up into the atmosphere, the height goes up, z. We have our x-axis here, which is the west to east wind, west to east. And we have our y-axis here, south to north, south to north. We also see here a wind profile, and this is actually the storm relative wind profile. If you were to draw the normal wind speed, the udz is up, the udz is positive, which means that essentially this whole thing, you can actually shift it back from here to here, meaning that you will have more or less like this, where wind speed increases towards the west. This is what the normal wind would be. The notion is, however, that as the storm moves east, it's seeing inflow from the east, which you can see here. As we have been discussing, right, this is what it should look like. The udz is positive. This shows the storm relative wind profile. A little bit more on that later because it's super important, okay? But the udz is positive. Wind speed increases in the x direction. Again, this is x. Let me draw it here. This is x. This is y. This is z. Okay? Let me erase this, right? Let's look a little bit what we have here. We have here this line. This is actually our tube, as we have drawn it before. This is our tube. Let me draw this tube here again, overlay it. And you can see this by the rotational vectors here. dudz is up. Wind speed increases as you move up into the atmosphere. So there is rotation here. It rotates in this sense, as we've already discovered or uncovered many times before, right? You can see this. You can see this in these rotational vectors here. So let me erase my yellow ones. It's the same idea. And what you also have here you have a thermodynamic updraft, as you can see here. This is a thunderstorm here. All right, which we now move towards this one again. This is our dw dy. The more you increase in y, the more w goes up, means dw dy is positive here, right? And the more you go away from the center of the updraft to the right, dw dy is negative. Okay, why? Because you move along the y-axis, vorticity is now negative. You can see this here by the clockwise rotations on the left side, or the south side rather. Vorticity here is positive. Okay, so this is what our tube looks like, because the tube lifts this horizontal vorticity into the vertical now, which is exactly what we have been discussing up until now. Okay. Now, what you actually see now is, because of this tilting process where the thermodynamic updraft here, you see the inflow in the thunderstorm here, which goes up. This is some precipitation, which actually goes downward, but let's ignore this. The thunderstorm grows vertically here. This arrow points the direction where the anvil is blowing off towards, which is actually towards the east. Okay. So what you see here now, that you have two locations in the thunderstorm where you have rotation. Positive vertical vorticity here, negative vertical vorticity here. And you have the thermodynamic updraft here. Essentially what you can do, since these are rotating here, there's a vort max here and a vort min here, but regardless of their sense of rotation, there's actually low pressure in the middle. They call this cyclostrophic. Let me write this actually. They call this cyclostrophic balanced vortices. Regardless of their sense of rotation, there's actually low pressure in the middle. So essentially you can write like two lows here. There's a low here and there's a low here. Let's erase this for now. But essentially you can do that. Now, if you look at it from the top, let me draw an arrow here. If you look at it from the top, you actually have your thermodynamic updraft here. This is the thermodynamic updraft where W is greater than 0. You also have here a rotation center. Let me draw a different color here. You have a rotation center here, which spins cyclonically, right? And you can write a low in here, right? On the other side here, you have the same. So let me draw another one in here, which also has a low pressure in the middle, cyclostrophic balanced vortices. But this one spins clockwise, anticyclonically. Now, if you look at it from the top, there's as much positive vertical vorticity inside the updraft as there is negative. Because if you draw, for example, like a Venn diagram, we can show this pretty easily. Right? Let me draw a Venn diagram real quick. This is the thermodynamic updraft here. And on the side here, you have this one and you have this one. If you integrate everything, there's as much positive vertical vorticity as there is negative. Which means integrated over the whole updraft, there's 0 net rotation. But what we want a supercell. So how do you get a supercell out of this? Okay, that's the main question, because we want net rotation to be positive. The net vertical vorticity should be positive because we want a cyclonically twisting supercell. Okay, the question is now, how do we get this? Okay, we're going to talk about that. Let me erase everything what I've done now. Let me erase everything here, right? All these things. Oops, my undo doesn't go that far, but no worries. Okay. Now, bear with me now. All right. You can see here you can actually now, let me draw my two lows in here. Like there's a low in here. There's a low in here, right? And you can see these two upward pointing arrows here, which means since because there's a low in here, they're essentially drawing air from beneath. And this is called a LPG, or lifting pressure gradient. We already uncovered in one of our previous videos that the pressure gradient force is responsible for moving wind from one location to another. And since there is a higher pressure here than relatively here, there's air moving upward here. And you can easily say, okay, yeah, sure, Jengis, but isn't air moving from the side as well? And from the top, right? Yeah, it is like this. Air is rushing in from literally everywhere. But since we have a thunderstorm here, we know that the air is buoyant here. The air is less dense here because it's warmer here. There's more moisture here. So the air here is less dense. So the net supply of air rushing into this low is more coming from below than anywhere else. Okay. This is the reason why. So let me erase everything, right? This is an LPG and this is an LPG. So let me put LPG here as well. LPG. Right? But remember, it's already drawing air from below, and we have a thermodynamic updraft here, which means that essentially you get 3 updrafts for the price of 1. You get 1 thermodynamic updraft here, and these ones are dynamically driven updrafts because of the cyclostrophic balanced vortices. Regardless of their rotation or sense of rotation, they have low pressure in the middle. Okay. Now, what we actually want is we want the supercell. Okay, and the supercell in the northern hemisphere spins mostly cyclonic. So what we actually want to do now is we want this vortex here, right? This vortex here to spin up more preferentially than this one, because we want net rotation, net positive vertical vorticity. We want this one to spin up more preferentially or preferentially faster than this one. And we can do that rather easily. We want the cyclonically spinning vortex to increase, right? We want d zeta dt in this one to increase, because as this rotates faster, it will draw up more air from below, and this one will essentially die out. But now we don't have this because, as we've already uncovered, or as we've already mentioned, this one and this one actually have the same of rotation. Why? Because the storm is moving from west to east. Since it's moving from west to east, it's seeing inflow from the east at low levels. As you can see here, it's seeing inflow from the east. Okay. Since it's moving in that direction and it's seeing inflow from the east, both this one and this one get the same supply of inflow into the storm. This is the inflow here. This arrow is the inflow. Okay. So we need to do something to the storm for it to spin this one preferentially up. Now we can easily do that by, bear with me now, what if we now no longer let the storm move towards the east, but we let the storm move more towards the southeast or the southeast, or perhaps even south? Why not? And did you already watch the supercell like on radar? Supercell on radar actually veers off to the right of its normal direction. There's a reason for that, but we're not going to go into that into the reason. But the consequence of a storm veering off to the right of the normal direction where a storm normally would go, the consequence of that is as it moves that way, right, more towards the right, this flow here now no longer rushes in here, but bear with me now, as the storm moves more towards that direction, the inflow is actually coming more from here now, right? It's coming more from in this direction. If it goes even south, right, the storm gets its inflow from this direction, right? So as it moves to the south, right, we shift the inflow now to be co-located with this sense of rotation, with this rotation center. And this has massive implication on our storm. Why? Because remember the stretching term, which we've initially thought was now 0? We actually have rotation now, right? We have vertical vorticity now. So the whole equation where we said that the advection term is 0 and the stretching term is 0, now they're actually no longer 0 because there is zeta. Zeta is active here. There is vertical vorticity here, which means that if we put airflow, or if we direct airflow now from here directly to here along the streamline, and we inject it into this vortex, right? We stretch this vortex into the vertical, right? And by stretching the vortex into the vertical, what happens? Say, for example, you have a rotation that's this wide, right? If you contract this rotation column where it's more narrow, it's like an ice skater. When they pull their arms together, right, vorticity increases as it appears. The cross-sectional area of the rotation column multiplied with its vorticity, the rate of spin, right, is actually a constant. So if you constrict the vorticity column in a smaller diameter, right, vorticity must increase to keep the constant alive. This is what's called the conservation of angular momentum. This is this process. So if you actually direct now airflow, because the inflow is now coming from the south, if the storm should move to the south, right, we would inject airflow directly into here, stretching the vorticity column, right, from a wider to a more narrower, right, which increases vorticity. And this is exactly what we want. We no longer have a 0 net vorticity, but we now have a vorticity which is net positive, which is exactly what we want. And now we have our supercell. Okay? So this is how it works. You have two cyclostrophic balance vortices. You direct your airflow to spin up one vortex preferentially over the other. And this means you would now have positive vorticity here. A lot of positive vorticity here. And because of the stretching here, we actually have our rotating updraft here, right? This is how supercells form. These are the ingredients that are needed for supercells to form. So now we've come to the conclusion of our video. We now know how thunderstorms lift the horizontal vorticity into the vertical. We know the consequence, what that means, because we now have two cyclostrophic balance vortices straddling the thermodynamic updraft here. And we can get a supercell by either letting the storm move to the right, okay, which they frequently do, or what we can also do is just change the wind flow, right? I mean, if the wind flow moves like this, wind speed increasing with height, but only the u component, right? We can do it a little bit differently. What we can also do is direct the inflow or the low-level airflow now to the north. So you have a wind profile which actually looks like this. We have like this, like this, like this, like this, like this, like this, like this. You have wind shear increasing in, we have wind speed increasing in altitude, right? But also the direction increasing, right? Which would, in theory, right, also give, if the storm should move to the right, it gets its inflow more from a southern component, which automatically spins this one up preferentially over this one, and you get your supercell there directly. So now we've arrived at our conclusion here, and now you can see how supercells actually form, which processes are needed for generating rotation, how the rotation is generated, and what are the mechanisms to spin up one vortex over the other when you have two dynamically driven vortices, two dynamic updrafts actually. If you spin up one preferentially over the other, you get a supercell. So I will send you off in a minute. Okay, see you there. Now, I know this has been quite a long video. I really hope you enjoyed watching it. And if you learned something, that would be very great. If you liked the video, as always, drop a comment in the comment section. Don't forget to subscribe as well for new content. It's a little difficult to explain such a difficult or such an intricate meteorological concept in a short time frame. I know it's a long video, but I really hope you can appreciate all the effort that I've put into it, and also that you cannot explain this in like 5 minutes and really understand how these processes work. Okay, so without further ado, I'll send you off right now. Thank you again very much for watching. Hope you liked it, and be sure to drop by the channel to look for some new content. Okay, see you in a later one. Bye guys.